Hello and welcome. In this lecture, we're going to work on one problem each in t-test, chi-square test, two-sample z-test and f-test. This will be sort of simple, straightforward problems where the sample distribution, the samples, and then the the null hypothesis, alternative hypothesis given, and you're asked what test to perform, just the numerical way of computing it out, right? So that's what we're going to do in this set of problems. So let's begin. So x is normal with mean mu, variance sigma squared. Sigma is unknown. Okay, so this is the t-test, right? So you don't know sigma. There are 16 IID samples, and observed sample mean is 10.2 and the sample standard deviation is 3, right? So x bar. So you have samples. Your samples are x1 to x16, which are normal mu sigma squared. Okay, sigma is not known, and then x bar is 10.2, and s squared, which is a sample variance, it's 9, right? So it's 3 squared, right? So 3 squared, which is 9. Okay. So you want to do a z-test with the null hypothesis being mu equals 9.5. Okay. And alternative hypothesis is mu greater than 9.5. Okay. So what is your test going to be? Reject h naught. This is right-sided, isn't it? So you're going to reject h naught if x bar is greater than c. And what is your significance level alpha? It's a probability that x bar is greater than c given h naught, and this we know is going to be the same as probability that x bar minus 9.5 divided by 3 by root n, right? So this is the sample standard deviation is greater than c minus 9.5 by 3 by root n, and that's roughly 1 minus ft15. Since you don't know the variance, this becomes the t distribution, and the number of degrees of freedom is 15, right? So ft15 of c minus 9.5 by 3 by root n, right? N is equal to 16, so root 16 is 4, so it's 3 by 4. Okay. So from here you can compute, that c equals 9.5 plus 3 by 4 ft15 inverse of 1 minus alpha. So this is the formula. Now if alpha is 0.05, this is going to become 0.95 and c is this, right? So this is the calculation you have to do. Now for doing this calculation, I always like to keep a Python workbook going with everything opened up. So we saw it was 9.5 plus 3 by 4 times st, which I've already loaded, the scipy stats as xt, st dot t dot ppf, right? Inverse of the CDF is ppf of 0.95, right? 1 minus 0.05 and 15 degrees of freedom. Okay, so I'm going to run this. I'll get an answer which is 10.81. Okay, so that's what is got here, 10.81. Okay, and since x bar is less than 10.81, we go ahead and accept the null hypothesis. Okay, so we will accept at a significance level of 0.05 with type 1 error probability 0.05, we end up accepting h naught. So once again, what does that mean? You have to always think of what that means. So if we were to repeat these kind of tests 1000 times, in 5% of the times, if we accept h naught, we would actually be wrong. We would have made an error. So that's what it means. Okay, so it's reasonable. We go ahead and pick up this h naught now. Okay, so this kind of problem is a very textbook problem on the t-test. We'll do a similar textbook problem on the chi-square test also. Okay, so this is chi-square test for one sample variance. So you can see here x is normally distributed with unknown standard deviation. Okay, once again there are 16 samples. Normal with mean mu, mean doesn't really matter, the variance is sigma squared, and you have a, okay, so this sample standard deviation S squared is given as 3.5 squared, whatever that is. Okay, the H0 is that sigma squared equals 3 squared, and HA is sigma squared is greater than 3 squared. Okay, so we're going to do what's going to be our test. Our test is going to be S squared is greater than C. Okay, so let's write it out fully. Reject H naught if S square is greater than C, or C squared if you want. Let's just take it like C squared. Okay, so this is the test and this alpha distribution. So now S squared has this distribution, right? So we know what the distribution is: n minus 1 S squared by sigma squared is chi-squared n minus 1. So this is the result that we know, right? So we have to work towards that. So the alpha is one probability that S squared is greater than C squared given H naught. So given H naught, you know the variance is 3 squared. So what's the probability that S squared will be greater than C squared? So again you do the same thing. This is probability that 15 times S squared by 3 squared is greater than 15 times C squared by 3 squared. Okay. So of course given H naught, so this is this distribution. This guy is chi-squared n minus 1. So this is 1 minus f chi-squared 15 of 15 C squared by 3 squared. Okay. So from here you get the standard thing that C squared is 3 squared by 15 f chi-squared 15 inverse of 1 minus alpha, right? So 1 minus alpha comes here, you do the chi-squared f chi-squared inverse, then 15 C squared by 3 squared is this, you cross multiply, you get this. Okay. So what is this? Again, we go back to our Python notebook. So maybe I'll do another expression here. 3 squared is 9, so you have a 9 by 15 times st dot chi-squared distribution chi2 dot ppf of 0.95 and degree of freedom 15. Okay, so this is the test. It's 14.9974. Okay, so it's really close. So you get 14.99. What did we get here? Some 7474, right? We can leave it like that. That should be good enough. So C squared is this. So you have to see if 3.5 squared is going to become greater than this. So let's check that out also. If you want a calculator here, 3.5 star 2. This will be 12.25. Yeah. Okay. Good. So since 3.5 squared equals 12.25 is lesser than 14.99 whatever, we end up accepting H naught, okay, at significance level 0.05. So you see the sort of predictability of these calculations. The critical thing to know is how the chi-square distribution comes, or the t distribution comes, or the z distribution comes in the z test. The method sort of remains exactly the same. Okay, I hope this is clear enough. So let's move on to the next problem. So here we have two samples. X is normal with mean mu1 and variance 3, y is normal with mean mu2 and variance 4. There are n1 equals 16 samples of x, n2 equals 8 samples of y, and the observed sample means are 10.2 and 8.2. Okay, So you want to do a two sample z test to check if mu1 equals mu2 or mu1 not equal to mu2, the alternative, and the significance level is given. So this is very again standard sort of question. So you have x1 to x16, which is normal with mean mu1 and 3. y1 to y8, which is normal with mean mu2 and 4. And x bar equals 10.2, y bar equals 8.2. Null hypothesis is mu1 equals mu2, alternative is mu1 not equal to mu2, and the desired alpha is given. So now the test statistic, as you know, the two sample z test has the test statistic as x bar minus y bar, and this okay, so let's write it down carefully. So you reject h naught if mod t is greater than c, right? So now t is x bar minus y bar, and we know this is normal with mean mu1 minus mu2 and variance sigma 1 squared by n1 plus sigma 2 squared by n2. Right? So this is the thing, so you can calculate it totally together, 11 by 16, isn't it? This is what it is. Okay, so I'm going to reject h naught if mod t is greater than c. Okay, so now t itself is normal, so alpha is probability that mod t is greater than c given h naught. So given h naught, the mean becomes 0, right? 0 and variance 11 by 16, and mod t is greater than c is the same as t being greater than c or t being less than minus c. So that is basically, so let's do the adjustment here. So probability that mod t divided by, right, square root 11 by 16 is greater than c by square root 11 by 16. So now this is normal 0, 1, so this is probability that mod z, so this guy is mod z, right, distributed as mod z, greater than c by root 11 by 16. This is going to become 2 times fz of c by root 11 by 16. Okay. So mod z greater than c by root 11 by 16 is either z being greater than c by root 11 by 16 or z being less than minus c by root 11 by 16, and these two are actually equal, right? So something is greater, these two are equal, so it is just 2 times fc of minus c I should put here, it's not c, minus c. Okay, so hopefully you see this is a standard picture that you do, right? So you have mod c, you have c by root 11 by 16 minus c by root 11 by 16. You're asking for this probability. These two are equal, right? The probability on the left side is equal to the probability on the right side. And so this one is fc of minus c and it's 2 times this. Okay, so this is the relationship between alpha and c. Okay, so if you put alpha equals 0.05, you divide by 2, 0.025, you take fc inverse. So you will get c to be equal to minus root 11 by 16 fz, maybe you can erase this guy is fc inverse of alpha by 2. What will this be? Let's find out. We have a little calculator here. Let's check what we are doing. Minus square root 11 by 16. So minus np dot sqrt of 11 by 16 multiplied by st times norm dot ppf of 0.025. There you go. 1.625. That's the answer. Okay. So mod t has to be greater than c. Okay. So the threshold critical value comes to 1.625 since 10 point, so mod t mod x bar minus y bar equals 10.2 minus 8.2, which is 2, which is greater than 1.625, end up rejecting H naught. This is the conclusion that you have reached. Okay. So again, the steps are largely similar, except that you have to sort of pay attention to the actual distribution of the test statistic, and then write down the formula for alpha in terms of the critical value, then go ahead and do the computation. Okay, hope this is clear. And the last two sample test we're going to do is the two sample F test, which is for the variance. Okay, again, it's a very similar sort of conclusion, but one needs to be careful in applying it and writing it down carefully. So x1 to x30 is normal mean mu1 sigma 1 squared, y1 to y25 is normal with mean mu2 and sigma 2 squared, and the observed sample variances are given here, sx squared, sy squared, and then what conclusion would I F test reach? Null hypothesis sigma 1 by sigma 2. Okay. So I'm going to write down the answer sort of directly. So T we know the test. Okay, so what's going to be the test? The test in this case is reject H naught if Sx squared by Sy squared is greater than some C. Okay, and we know that this Sx squared by Sy squared for sigma 1 equals sigma 2 is actually F 30 minus 1 comma 25 minus 1, right. So 29 comma 24, right, n1 minus 1, n2 minus 1. Okay. Okay, so we know the F distribution is not symmetric about 1, and one needs to pay attention to that. So it will have like a sort of a distribution like this, right. So and then it will be around 1, right. For the F test you have to look at it, and then there will be this 1 plus CR and then the 1 minus CL, and I will have this area as alpha by 2 and this area as alpha by 2. Okay, so one needs to pay attention, solve two different problems here, that's important. Okay, notice this is two-sided, and I am expecting this Sx squared by Sy squared to be close to 1 if it is if null is true and it's away from 1 and away from 1 in this particular way. Okay, so one needs to pay a little bit of attention here. So alpha by 2 for the left part equals F of 29 comma 24 of what? Of 1 minus CL, isn't it? So CL equals 1 minus F of 29, 24 inverse of alpha by 2. Okay, so let's do this one. Okay, so this test also is wrongly written. Okay, so this has to be changed to if Sx squared is greater than 1 plus CR, or Sx squared by Sy squared is less than 1 minus CL. So this is the sort of test that we have. In this case, Sx squared by Sy squared is ending up being greater than 1. So we may calculate this, but that's not going to significantly affect us, because Sx squared by Sy squared in this sample is working out to be greater than 2, right, in some sense. So it's enough if we find CR. So let's work on CR. So alpha by 2 is F1 minus F of 29, 24, okay, of 1 plus CR, isn't it? So let's just try that. So this implies 1 plus CR equals, F of 29, 24 inverse of 1 minus alpha by 2. Okay, so we can pick alpha as 0.05. So this will give me 1 plus CR equals what? So this is the critical thing. So let's try and look at that. st.f.ppf of 1 minus 0.05 by 2. Okay. Okay. Oh, okay, I have to give the degrees of freedom. Of course, 29, 24. Sorry about that. 2.217. So that's interesting. So 1 plus CR works out to 2.217. Okay. Now in this actual case, Sx squared by Sy squared equals 11.4 by 5.1. Let's try that out. 11.4 by 5.1. That works out to 2.235. Oh, so close, isn't it? 2.23, 11.4 by 5.1, which is 2. Let me check that again. 2.235. It's greater than, since this is greater than 2.217, we end up rejecting H naught. Okay. So this is the sort of calculation you need to do for the F distribution. Once again, this is asymmetric and you're comparing with respect to 1. It's a different sort of distribution, so you have to pay some attention in the calculation. You can sort of see where your actual sample ratio came, and from there you can decide whether you want to find CL or CR. Okay, so that's always useful to do. And Sx squared by Sy squared, you remember the 29 comes first. So that's the way to remember what comes in the numerator and what comes in the denominator. Okay. So hopefully you saw a set of 4 problems which worked out cleanly, simple textbook problems. In the next lecture, we'll see slightly more complicated real life data sounding problems. Thank you very much.